Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hear me? Hands up, anybody that can't hear me. Don't say that, Scott. So welcome to our first brown bag session, the Robotics for Instruction session. We've got about just up to an hour maximum on this. So we're going to get going, and I'll try and keep the pace up. Contrary to the little introductory text in the Faculty Summit description, I've actually been blessed with 3 additional presenters, all professors. There's Professor Jim Hamlin from Georgia Tech. There's Professor Illa Norbach at CMU, close. And Professor C.J. Taylor at UPenn. So I'm going to just keep my talk real short to about 10 minutes here, and equally you're going to hear 10-minute talks from these professors, giving you their thoughts and my thoughts on how robotics technology could be used in instruction. I put abbreviated for Faculty Summit because my talk, as I'm sure all the professors' talks, are shorter versions. We can talk for hours about robotics. So if you want to talk to us for hours about robotics, we can do that after this event. We're just going to give you a quick kind of machine gun run through our thoughts on robotics for instruction. So without further ado, in a way, Bill Gates stole my pitch for me this morning. So I'm going to mail him this afternoon and complain about that. Computer science is in decline. This is a real challenge for Microsoft, as you heard this morning in the plenary. And this is what's driving my thinking, and I represent the External Research and Programs group here at Microsoft Research in embedded systems and robotics. And so I'm seeing these graphs as much as the rest of us in the company, and it's a real concern. Computer science is in decline in terms of numbers, attracting students to computer science. And we've had a little bit of discussion about that problem earlier this morning, and I'd like to encourage a little bit more, especially in the context of using robotics to perhaps try and address this challenge. So why robotics for teaching computer science? So computer science is in crisis. We've talked about that this morning. But computer science is also in transition. I think it's evolving. There's quite a debate going on in the computer science community, perhaps driven by this crisis, but also because of the state of the art of the technology. It's getting some level of maturity these days. But there's not a consensus around what computer science even is today. And I think there's some interesting debating points which perhaps we can tease out later. Perhaps, in my view, is that the first level and second level computer science is where the greatest need, and that's where Microsoft's priority is. That's where I fit, in a sense. But perhaps there are alternative positions in the room. We'd like to hear that. There are interesting trends to look at in computation, computing generally. There are increasingly applications that deal with the physical world. It's less maybe interesting things in the traditional data processing world, although I'm sure other people would argue that. The whole point of this brown bag is to create a bit of discussion here. Perhaps you won't agree. But I think that perhaps some of the most interesting applications that are emerging are those that deal with the physical world. Computation today is inherently applied and it's becoming pervasive. We're seeing computation being used throughout our environment and throughout our lives. And we're seeing increasingly devices and general-purpose computers working together. I don't see general-purpose computers going away, but I do see an increasingly large and diverse and interesting ecosystem of device-centric computation happening, working together with our general-purpose PCs today. Robotics offers a number of different attributes which I think could be advantageous to teaching computer science. I think robotics is cool, and I think a lot of people will agree with me. I think a lot of students will also agree with that position, and we've actually got some experiential evidence to see that's proven. I think it's engaging in deep ways, deep personal ways, deep human ways, in the way that human beings relate to machines that are autonomous or semi-autonomous. So it's a very appealing in a fundamental way to human beings. And they have a wide appeal. It's not just the geeky people that want to work all night. Robots appeal to a broader spectrum of people. Robotics offers the physical embodiment of abstract concepts. This is important because as computer science can be a relatively abstract field, then if we can embody some of those abstract concepts into physical manifestation, this really helps in the learning process. You can use robots to encourage team-based learning and lab-based learning. Good ways to encourage better learning, greater learning, make the classes more attractive. There are some gender and diversity benefits in robotics, I think. It can be less elitist having robotics, less theoretical perhaps. Challenge me on this later. We think that robotics may offer the chance of a deeper learning and richer learning. Again, perhaps to be confirmed. I offer this as a hypothesis for that moment. We have some existence proofs, but perhaps no scientific evidence, or a little bit of scientific evidence. Some of the professors I know today have got some scientific evidence for this. There's a full talk that's available online that I'm not going to go through today. I just wanted to flash this up as the scope of this. So look out for this talk in your after the event, and I'll encourage you to read it, and I'll be happy to speak to it at another time, but no time today. So let me just give you a taste, though. Educational robotics, for those of you who have even thought about robots in teaching, may be familiar with a lot of these logos. A lot of them are at the K through 12 level. There's hardly anything here that's applicable at the undergraduate level, although some are. We do see a lot of Lego up here. Lego's being used in undergraduate level. But notice there's quite a diversity of organizations. But if you look at all the schools, and this is just a short list that I got off the UMass Lowell site, this is a selection of research universities doing various diversity of robotics research. There's a very large community here in educational robotics. It's perhaps not particularly coherent, it's particularly not got a single theme, but there's a very active field here. There are some challenges in bringing robotics, I think, to the classroom, especially to the CS1, CS2 classroom. There's price concerns. Perhaps the most popular robot in universities today is a $10,000, $20,000 robot. This is good for maybe researchers, but is not very effective for teaching large numbers of students. Performance. There are, I mean this in a rich way, I don't mean just the speed of the robot, but there are very interesting attributes about what makes a robot compelling in the classroom in terms of how it performs. If I could just summarize it, perhaps if you had a sluggish robot, and many of today's robots are fairly sluggish, fairly slow, this actually makes it less compelling than it otherwise might be. So a nice, quick, responsive robot is very important for the classroom. Whoops, I hit 2 there. Durability. Durability is very important for the classroom. I was just in the Conference XP class using tablet PCs, and people were talking about what happens if you drop a tablet PC. Well, if you drop a robot, if you drive a robot over your foot or over your classmate, then I know I don't mean about durability of students here. The durability of the robot, though, is very important because of perhaps price concerns, economic concerns. But I don't want the robot to keep breaking down. Robots are fragile creatures today. The state of the art of robotics is at the stage where these things need a lot of love and attention. And teaching professors don't have time to keep fixing robots. Some of the really dedicated ones do. I'm looking at Jim here. But that we really need, for any mass adoption of educational robotics in the classroom, more durable devices. Flexibility. If I just got a robot that does one thing, maybe it follows a white line or a black line, you've all seen these things, that's not a flexible robot for the classroom. Maybe that's one scenario that you want to explore, although I think personally it's a little bit tired, that scenario. But a robot that can adapt to many different tasks, do many interesting different things in the classroom is really important, I think. And last of all, ease of use. This is another big, rich concept, and ease of use sounds a bit simplistic. If I can summarize it in saying, though, if you were a professor that maybe you'd like to use a robot, you'd like to try this idea that you heard about at Faculty Summit, try a robot-based class in my classroom, imagine all the challenges that professor has to face. They have to be probably a robotics interested in robots in the first place. They have to go and be an amateur roboticist, have to get into the field and understand the field. It's not something they can take off the shelf. So ease of use of robot technology in the classroom is a pretty daunting challenge. I actually wanted to go into this a little bit more detail, just very quickly. The sort of adoption impedances, as I put it here. The opportunity that we're seeing is not necessarily in the people that are already signed up to use robots in the classroom. That's a small number of professors in the great scheme of things. They're good professors, we love them, we think that's important, we want to encourage those professors to continue using robots in the classroom. But the bigger opportunity and the bigger challenge is for those professors that aren't using robotics and feel that robotics is too difficult to use in the class today, or maybe haven't even thought about using robots in the classroom today. So I think the opportunity or the need for robotics technology in the classroom is not the existing robotics professors, it's actually the people that are not using robots today. And the number one item on that would be, for those professors, well, do I have to change my curriculum to use your robot technology in a classroom? And I think a really important challenge for the community in working in educational robotics is how do I adapt robot technology to existing classroom? Is that just a pipe dream that Stuart's talking about, or is that something that we can actually address? And I'd like to suggest that that's a research topic that we can try and solve. There are many different professor perceptions and needs. Perhaps we can drill into those a bit later in the discussion. And equally, student perceptions and needs. What do students think of robots? What do professors think of robots? How do people see robots? We should open that question to the floor later. There's some grand debates in computer science and robotics that are applicable, that are challenges to adopting robots in the classroom. You know, how much theory should we teach? How much application should we teach? Well, is robotics the same as computer science? Is robotics even a part of computer science? What has robotics got to do with computer science? It's all about mechatronics, isn't it? It's all about engineering. And I would argue no. I think today's robots and robots going forward increasingly are dominated by the computer science, the software elements within those robots. And certainly I think there are many interesting challenges in the mechatronics, but equally there are amazing challenges and interesting work to do in the software side of robotics. And last but not least, there's an existing robotics ecosystem, a marketplace for robotics technology today. There are manufacturers already building robots. Some come and go, some are out there and been there for a long time. But there are some attributes that I've listed which are very relevant to this marketplace. We think that we'll see some new companies emerge in this area, and I hope some of the existing companies will adapt to rise to the challenges that I'm highlighting. So that's the end of my talk. I'm glad nobody's interrupted with questions, thank you, because I'd like to encourage you to think about the talks as we go through, about 10 minutes each from the three professors. Here's my list. And let's get together in a panel and have a discussion about this towards the end. If you need to ask a clarification question, then do raise your hand and we'll get that addressed immediately. Thank you for listening. Jim.
I'm Jim Hamlin. I'm from Georgia Tech. I'm actually in computer engineering. And we've been using robots in our courses for around the past 6 years or so for some of the same reasons Stuart just went over. We wanted to have more student interest in the projects, not necessarily have a goal of teaching about robots. We've actually used them in 3 large undergraduate classes at Georgia Tech, and it's sort of been the first class and the last class in the whole curriculum where they've shown up most. I would kind of argue that Comp E and CS students need some projects with a mixture of hardware and software. Certainly Comp Es need more hardware. In the CS-oriented courses, I would argue have more software content. Some of the other things Stuart just went over, the funds are limited for school, and it can be tough to support large numbers of students. Our first class we've used the robots in actually has up to 300 students a semester in. So instead of like one research robot that might cost $20,000, what we really needed was 20 robots, or even more than that. Even if we use groups, we still need 20 robots. Some of the things I'm going to talk about were funded by the recent Microsoft embedded RFP to buy the parts. Our overall approach in the robot projects has been to concentrate on the higher level problems more. So we typically, if I had to think about what's happened in all the projects over the years, we pick a robot base, we add a computer and some electronics, pick out some sensors that are going to make the robot a little more interesting. And then the largest part of the project is really in developing the software and working with the hardware to control the robot to do some interesting tasks for the project. One of the things you can do is if you have more durable, expensive parts, they can be reused several times by students, and we've been successful at doing that. I'll show you some of these examples in a couple of seconds here. Some options for robot base, I have to go through these pretty quickly. Build one from scratch. That's probably a bad idea. The students will spend the whole semester just building the mechanical parts of the robot and not really have time to work with the higher level sort of software issues that you really want for the project. There are some hobbyist robot kits. They tend to have a pretty small microcontroller in them, and I don't think that's really probably what you want in most courses. Certainly the higher level courses, it's a little too simple. There are some low-cost radio-controlled toys and models that you can add a computer to make an interesting robot. I've got a couple examples of these in a minute here. And there are some small low-cost commercial robot bases, and I'm talking low-cost here is under $1,000, somewhere between $300,000. Here's one we built in the first class. Off-the-shelf radio control parts. Uses radio-controlled servos and a plastic disc. And this is the one we first used in our first digital laboratory course. And we have built 20 of these, and we had about 300 students that use these. Basically, they had to program them and interface them to different sensors each time. Yeah. That's a 10-inch circle, about 10-inch diameter circle. This is a radio-controlled truck that the students added an e-box to. I've got another slide on the e-box in a couple of seconds here. It actually runs Windows CE and had wireless networking on it. It's a little hard to see it underneath there, but you can see a tire sticking out of the corner there. That's a Radio Shack radio-controlled truck, which they use the motors and batteries and control circuitry from. This is a radio-controlled model that you can buy. It's actually a Hummer, and they put a CMU cam on that and a computer board and use that to control it. The nice thing about the radio-controlled models is they use a 1-bit digital pulse width modulated signal standard to control everything. It's fairly easy to interface to. Here's another robot base, the AmigoBot. It's made by Active Media Robotics. Was actually designed to be controlled by a serial cable from the PC, but you can use the serial interface and add a computer board to it and have a little robot. It's got motors with drive electronics, shaft angle encoders, and sonar built into it with a microcontroller. These are all undergraduate projects that students have built. Here's another one where they used a slightly more advanced computer board, and it's more like a PC on a board. And they actually, undergraduate students actually built a teleoperated robot here in the lead, and the other robots follow it automatically, and they exchange messages over the wireless network. ER1's another popular robot base, kind of interesting concept here. You get the base and you put your notebook computer on it. It just plugs in with the USB cable. They give you all the drive electronics and a battery for it, and that's around $300 without the sensors. And even the undergraduate students have been able to build several projects with this. The one on the right is one where they added sonar to it to explore a room and a camera. What kind of computer do you want to control your robot? If you're going to reuse the parts, it's nice to have a really fairly powerful computer, which is maybe overkill for some of the projects, but will work for all of the projects and can be reused. You can use embedded computer boards or a notebook. You have to worry a little bit about power consumption because it's going to run off batteries. I would argue that for the more interesting projects, you probably need an embedded operating system because you probably are going to boot from flash, not have a disk drive. Probably have multi-threaded solutions in your applications. Wireless networking is awful nice to have available for communications and remote control of the robot. So you add all that up, you sort of want a nice operating system there. eBox is a nice little embedded computer board, runs about $180 with a discount. You can run Windows CE. Here's a higher performance embedded computer board. This is more like a PC on a board. Runs about $900. It can run Windows CE or XP embedded. Of course, the more powerful computers take more power and maybe a bigger robot, so you got some trade-offs there. Just a couple of slides left here. Here's some interesting sensors for robots. And for under $50, you have some pretty interesting sensor options out there. And I've restricted it to ones that have digital outputs that are very easy to interface for undergraduates. There's a line tracker module. Like Stuart said, that's a little passe anymore. But the other interesting ones are there's an IR proximity detector that tells you if anything's close. From left to right there, there's a wheel encoder add-on for $20. GPS modules around $100, but they don't work inside usually, so you have to have an outdoor robot. Sonar to measure distance, IR detectors to measure distance, an electronic compass module, and you can get cameras, fairly low-cost color cameras for under $50, that, sort of like the modules that go in the cell phone, same chips. Okay, so the things I'd like to say in conclusion, I think it has made our projects more interesting. Our class evaluation numbers have gone up, and the complexity of the projects has improved since we did all this. And I feel like the students are getting a pretty good experience out of the robot project as far as writing the software and the various things they have to do to solve this. There is a discount program that Microsoft has set up, the Hardware Empowerment Program. If you haven't heard about that, that helps you with discounts on the computer boards. And as Stuart said, I think you could use a new educational robot kit with some more capabilities at a nice price. Yeah. It's our first computer engineering course, which would be the second year, and also the senior design course, which is just about the last course they take.
So they have done already computer organization, digital logic design, and all that?
Well, our first course is digital logic design. And they actually do some digital logic design with the robot because it has an FPGA on the board, too. Okay, because I need to move on.
Thanks.
Right.
Yeah.
Thank you. Hi, everyone. Thank you. Well, I have to apologize to a few people in the room who have seen some of these slides before, but there are new slides at the end, so I'll blast through the other stuff. One point to make just about educational robotics, Stuart was mentioning that possibly the first most important hit point for Microsoft is introductory CS classes, and that's probably where the retention problem starts. Although I have some comments about that in our discussion. There's some debate about where the retention problem is occurring for gender retention and for overall CS retention. But I see great opportunities for educational robotics in everything. On the pre-college side, high schools in other words, and at the undergrad level, grad level, and lifelong learning in terms of adults who are trying to learn about technology. Just to give you a very, very brief flavor of that, I'm going to run through these. But we have students in high school classes, things like what Matt Mason used to teach in Andrews Leap, who build robots. And by building robots, they learn a whole lot about teamwork, problem solving, and of course about programming as well. We have contests such as BotBall, in which people work together as teams, and they meet people nationally, and there was even an international BotBall contest. There was one in Qatar this year in the Middle East. At the undergraduate level, there's a huge number of activities available. We've done some curriculum development and testing with freshmen, and even with some kids who are going to their freshman year in college. And there's a number of different kinds of activities there. There's classes in which robots are sort of a side activity, and there's classes in which robots are the principal activity. This is an example of a class where programming the robot is the activity of the course. And the course presupposes that you have good programming skills going into the course. Whereas this is an example where they're building a simple robot out of foam core and glue. And in fact, it presupposes they don't know how to program. And we're going to teach them a little bit of programming. And they're going to gain some empowerment, both with respect to mechanism and with respect to software. And then there's project classes that we use. There's graduate students and projects that they do. And there's, in the lifelong learning sense, things like museums, where you can create robots that are interactive, proactive with humans, and you create a space where families can have more interesting communication between the members of the family. So you actually trigger interesting conversations between the father, the mother, and the children about technology and about the role of the child in technology. And we have shown some really good results in terms of fostering that kind of communication in a museum setting. Okay, why robots are good? This sort of echoes exactly what Stuart said. I'll blast through it because many of the points, I just agree. strongly with what both of those previous speakers said, Stuart and John both. On the gender retention side, we've shown some early results that I think are very exciting, that showed that the all-women team actually do better in many cases than the all-boys teams do in our coursework. And furthermore, that we have a lot of cases where the women start out with a bigger perceived barrier to success because they didn't have quite as much training in computer programming. And by the end of the course, they've actually overcome that. And they've caught up with the boys. And that's a major gender retention issue in introductory computer science classes. There's another side of it, which is that I think mechanical empowerment is important. Now, there are going to be some classes, and John pointed this out, where you can't spend a week building the robot. And that's okay. But then make available a fast build kit. Make something available so that at least in 2 or 3 hours you can put together the robot. And the reason that matters is because it really does empower the students so that they understand the robot. It makes it much less of a sort of alien creature to them. Much more of something where they understand what parts went into it. And when it breaks, it means they can fix it, which is a big deal because that offloads the instructor greatly. So fast build kits, I think, are the right step forward in terms of mechanical empowerment. Remote programming is something else that I think I've gained from. I used to teach classes in which all the programming was done on a laptop on top of the robot. And we have a few jokes in my lab about the ER1 where you're sacrificing your laptop to your robot. You know, get your code wrong and it will stab itself and kill its LCD display. More recently, we're going to a remote programming model where you're really programming on a laptop off-board the robot and you're communicating with the robot. And as wireless networks have become much, much more effective, especially ad hoc style networks, we're finding that actually works really well now. Vision-centered perception is another big one. I agree that you need higher-end processors, especially because it's so exciting to be able to do something with a robot that can see the world. You can chase a ball. You can chase your little sister into the bathroom. I mean, you can do things that are actually dramatic and interesting, far more so than anything you do with sonars and infrareds. And so we need processors to be powerful enough to allow us to do interesting vision work on the robot. That, in terms of the rhetoric of a good narrative of coursework, it gives you a project that people write home about. They tell their parents about. Mom, Dad, you'll never believe it. My robot recognizes my face now and smiles at me. Come see this in the lab. And we need that kind of grab. Okay, enough of that. 2 quick education examples, and then let me give you an idea of what we're working on now to hopefully try and provide a solution. This is based on, this was done by Learning Research and Development Center at University of Pittsburgh. And it's just an example of the kind of result that excites me about the role of robotics. We do frequency-based coding analysis of interviews with students and self-reports of students as they maintain diaries. Week over week, they report programming and mechanics as the areas where they expect learning to occur. Week over week, we ask them at the end of the week, what did you learn? And we code based on what they said they learned. Check out the flip-flop. Teamwork and problem solving are just as high as programming and mechanics. Identification with technology is also way high. These are very exciting results. And the reason is a couple of different things. One of them is lifelong learning. Problem solving, teamwork, identification with technology are all critical lifelong skills. They have nothing to do with whether you choose to go into computer science or not. On the other side of it, teamwork, problem solving, point of view are all areas where, in fact, girls shine over boys. And so if it's the case that you're having significant lessons learned in those areas with robots, as opposed to a static computer screen that you're programming on, then there's reason to believe that, in fact, robots can serve as a vessel for inspiring women to do more in computer science than they do today. And so in terms of gender retention, this is a big deal. One final thing, and then I'll talk about what I'm doing now. Just raw quotes from 12th graders who've just taken their first programming class ever on a robot. So they did not know how to program, and then they programmed on our robots. They're raw quotes, and the bottom one deserves to be on a calendar, right? Doing something slow is better than doing it twice. That's pretty cool. Another one that's kind of amazing for high school students. Yeah, that's a good one. Teamwork is hard, especially with varying levels of skill and different personalities. Can be rewarding only through compromise. High schooler. Let's see, they're getting the idea of different levels of skill and personalities, and they're getting the idea of compromise, and that teamwork can be rewarding. And boy, if you could teach everybody that would be of great value to society. Okay. Now I have just 3-4 slides on what we're doing right now. Stuart asked me to describe what we're doing, and I want to say that the work we're doing now, although previously we had a great deal of funding from NASA, this work I'm describing now has actually been funded by a little tiny seed from Microsoft. So thank you to Microsoft for making this possible. We're doing these 5 different things, And the general idea behind this is, I believe we've hit, and I'm using the wrong metaphor here, an elbow in the curve in terms of where technology is with respect to what kind of robot kits we can create and what kind of robotic community we can have on our hands. I believe vision and microprocessors have become advanced enough. And in fact, hardware and rapid prototyping facilities have become low cost enough that we can actually make a ground-up new kind of robot, and we can create a new kind of sort of internet-enabled firmware for that robot, such that we can all teach with robots that are much easier to use. The idea is not for us to proffer you one solution and say, this is the robot, go buy it, we've licensed it to company X. The idea is that we create a set of recipes on the web that everybody can change and use as they see fit, so that you create sort of a community of people who can design both the physical side of the robot and the software side of the robot, but that you have some interesting interlingua between them. Reference design library is one of the big activities here. Ben Brown is actually working on this, and some of you may know him. He actually worked on the Hopper with Mark Raber's lab back when Mark Raber was at Carnegie Mellon University. His task is to create a series of robot recipes for us. Robot recipes we can publish on the web that use only off-the-shelf parts available on the web. Things like McMaster-Carr may carry and Home Depot may carry, DigiKey may carry. And in so doing, he's creating robot recipes that are easy to build but ingenious in their mechanical design. So we want interesting robots. And on the right, we just have a rendering of two of the robots he's making right now. One is an interesting base that consists of two small bicycle wheels, 14-inch wheels, friction drive, because it's very inexpensive that way. And the other is an interesting prismatic arm idea. We have two different arms. One is a 5-degree of freedom Revolute kind of balanced arm, and one is this interesting prismatic arm. This one's designed to be able to deal with things like elevator buttons, so that you can actually telepresently explore a space. There's a camera on the end of the arm as well as a fingertip. So you can't grab anything. It doesn't have grippers yet. But the first version will have a finger and a camera right at the finger, so you can go push things or make a mess of somebody's desk by pushing everything off of it. OK, so he's working on that, and there's 4 proto-recipes that we're working on. One is this sort of telepresence chassis and the arm. The other is a small, low-cost tabletop robot, and another was a fixed robot. Each of those is supposed to cost less than $300 to build. That's the dream. I'm sorry, $800, including the processor. The next one is a robotic electronics package. For this one, working very closely with Charmed Labs, which is a company that put together the BotBall robot processor. And very briefly, the slides will be available, I believe. It's an ARM9 FPGA hybrid, so it does have an FPGA on board because we think pedagogically that has great value. But in terms of cost, it really cuts down our cost. Here's the exciting part. It's 2 stacked boards. And they've got the processor and they've got the FPGA. The FPGA is the circuit for all the power electronics and all of the processing. It's got Ethernet, it's got wireless, it's got digital I/O, all 12-bit. It's got servos, 4 MOSFET motor drivers, so they're very small, high-efficiency motor drivers. They don't need heat sinks. And it has onboard switching power regulation. All you do is you plug in as many Radio Shack batteries as you like. And it does the high-efficiency power switching for that, of course, using the FPGA. And the target price, the bill of materials we're looking at right now is $100 and something. And the hope is to be able to have him at least sell this at first for $200 and something. That would be the dream. So it would be very interesting because as you compare this to a single board computer, yeah, this is about the cost of a single board computer. But this is not just the computer, folks. This is the computer. It's the power modulation circuitry you need for a robot. It's all the analog and digital I/O you need for a robot, right? And so that's exciting if we can get there. OK, 1 minute. I'll go quickly now. Robot connectivity. The idea on the software side is create a set of open source firmware that talks to that arm such that you can build any robot you wish. Ideally, you start with one of the ones we'll have in a recipe. You take this processor, you plug it into the processor, turn it on. When you turn on the processor, it seeks, figures out all the SSIDs in the area, tries to connect to our server. Once it's connected, green light comes on. So the idea is even if you're not an internet expert or a programming expert, you immediately have a robot that is alive, that you can go to any web browser, talk to it, and control it. And then, of course, if you are an expert, you can do much more than to simply control it. You can program it. But the idea is to have sort of out-the-box internet connectivity. We'll see where we go with that. There's a curriculum design effort that we have at Carnegie Mellon University. And we also have some friends at MIT, Daniela Rus, and at Columbia, and at UMass Lowell, Holly Yanko's there, and Peter Allen at Columbia. They've all been given an earlier version of a robot by us, a rover robot, and they're going to develop curriculum along with some of our students. OK. The turkeys involved in this work. It's Carnegie Mellon. University of Pittsburgh will do all the education evaluation. Charmed Labs is working on the processor board. Lauder Shelley is the graphic design firm that did all of our previous educational work. And thank you to Microsoft, Xilinx, Creative, and NASA, and Google. I think that's it. The take-home message from this is it's an example of a project where we're trying to create a community. And so those of you who are interested in that kind of community, please do communicate with me. Google on my first name to get to my email address, I guess, Ela. But I'd like to know of your interest because we're going to be interested in finding beta testers for the February, March timeframe in the next year. Okay. I'll stop.
Thanks, sir.
Yeah.
I guess, is this on?
We've finished the z-axis and the x-axis. I'm building my
Okay. I just put together some very brief comments on some of the stuff we're doing at the University of Pennsylvania on a project that we're calling Rocky for Remote Objects Control Interface. I'm CJ Taylor, the last name. The people who do the work are, of course, the top two names. So those are the people you really want to talk to. So what's Rocky? Rocky is something that sort of sprang out of some of our research needs and the ability to program moderate-sized teams of distributed robots, UAVs, UGVs, blimps and the like. And here's my one gratuitous robot video. We sort of made a very early decision to try to build a new kind of framework on top of .NET or other types of, basically to take advantage of the kind of object-oriented facilities and capabilities that we thought we could leverage later on. So it's strongly typed, it's object-oriented, and it gives a sort of a principled way of going about programming distributed ensembles and doing remote programming. So our idea is fairly common. What we do is we think of applications in terms of collections of software ICs, and these software ICs are objects that are built on top of .NET. So we build tasks by composing lots of composing modules and connecting them both within nodes, across nodes, and so on. The nodes are connected together via pins, which are also strongly typed, and the advantage of doing a lot of this stuff on top of an object framework is that we are able to use a lot of the reflection capabilities that are built into .NET. So we have systems that are able to go out and automatically, first off, we automatically build ad hoc peer-to-peer networks. Nodes come online. They automatically advertise themselves. They tell you about what they're running. They tell you what modules they're running. The modules tell you what kind of pins they're running. So you can do fun kind of self-discovery, self-configuration, remote programming. And some of the stuff we were interested in was distributed database. A lot of that falls out because you're living on top of an object system. We have the way that we think about programming using and configuring this network is through a browser interface. The browser would populate something on your left. It would tell you about all the nodes that it's found. It would tell you about what kind of task you could run. It would tell you about the modules that are running and who they're talking to. You can also use the browser to go in and query individual modules and various pin outputs at various levels of, depending on what you're interested in. So they're just doing a browser. They're populating some of the image information, GPS information, overhead information, so on. That was one of the things that we were very interested in being able to do. Again, this wasn't just restricted to robots. We're also interested in being able to program distributed sensors and actuators. So here, for example, is some of the stuff we do with smart camera networks. Sort of same idea. You want to have small, distributed, embedded systems all around the place, and you want to have a way of building applications that are made of these small pieces of software that interact in very prescribed ways that you can reason about in a good way. So here, for example, is a system that has 4 cameras and 3 sensor nodes, and they automatically see each other. They talk to each other automatically because they discover each other automatically, and then they can do things like automatic self-localization. So then you can play games like surveillance and yada, yada, yada. Okay, some very brief comments on some of the stuff we're doing right now. We're working on the next version of our open source release. We have a current version up on the web that we're hoping to improve greatly with some of the funding that Stuart has kindly provided us with. As has been previously mentioned, we also have some efforts involved in developing designs for low-cost indoor mobile platforms, and also sort of making some of our outdoor designs. So the cloud busters that I showed you earlier, were based on the kind of RC platforms that Jim had been talking about. We want to make those designs commonly available as well. One of the things that we're doing on our indoor mobile platform is we've developed a very simple robotics bus based around CAN that gives us a way of doing simple. It's a very simple set of circuits that allows us to incrementally expand the capabilities of the robot in a very easy way using very simple interconnects, very simple, very low-cost boards. And the idea really is we want to have this sort of low-cost but somewhat performant backbone that acts sort of as a spinal column, and then plug it into to something like an embedded PC running XP embedded CE or the like, or a laptop in many cases, which would be doing your higher computation things like vision processing, which is something that's near and dear to my heart. So I'm very pleased to see that Ella also thinks that's a good way to go. Yeah, we'd really like to have systems that are running around using webcams as their primary interface, and that's one of our goals going forward. Okay. So some of the experiences that I've had with this program, and at this point I'm teaching mostly senior design type students, is that the modular design sort of helped me in a number of ways. And I think this is common to a number of these kinds of frameworks. First off, it sort of gives students a very simple model that they can use to understand what's going on in the robot. It's sort of very easy to write down a circuit diagram of what each piece does, and that allows students to understand the entire design, but also then drill down into particular pieces without necessarily having to go and write your own PID module for controlling the motors. You can say, look, your job in life is to do vision-based recognition. Your module has these inputs and these outputs. Go to it. So it enables students to get up to speed very quickly, and enables students to contribute code and to collaborate, and that has actually worked out pretty well. The other advantages, I guess I'll skip for the moment, sort of have more to do with how they get used in research contexts. So let me stop there. And
okay, gentlemen, should we come to the vote and see if there's any questions from the floor?
So do we start with incendiary questions, or?
Any questions from anybody at all? Yes, good.
All right, so I've been in this game for a long time too. I feel your pain entirely. I agree with anything and everything that was said, except that where are the faces and the arms? Where is the upper body? So you said my robot smiles at me. What does it smile with? None of the things we saw could smile with anything. So I'm really interested in seeing how, and especially if you want to get girls into this, but I'm really interested in seeing platforms that will actually have however simple and cheap of an upper body you could put in there. It has to be light, it cannot be dangerous, but I'm not seeing that mentioned at all.
Yep, it's on. Okay, right. Well, 3 comments actually. Two kinds of lessons. Okay, it's 2 comments. One is 2-part. 2 kinds of lessons that worked really well for me with girls is when you finish building a fast build kit robot, the first thing we do is we have each team dress up their robot to make it unique. Because when they build a fast kit, it looks exactly like all the other ones that just got built. And immediately, when they spend a few hours personalizing it, they usually create some kind of backstory behind that. Each team builds 2 or 3 robots usually in my classes. So if it's 3, then they decide that they're the 3 Pokemon players, and they dress them up that way, and voila, you have 3 robots that are different from every other robot in the group. The other big one is one of the first lessons I have them do after they learn how to script for the robot, essentially command the robot to do a sequence of things, is a play. That works exceedingly well with the girls. So the challenge is choreograph a play that you and your robots will perform for us, the audience. And again, that's an excellent way to get them involved with understanding how they can make the robot have some drama and have some affect. Now, none of the robots I've built actually have anthropomorphic characteristics, and that's a really interesting point that you make. I've actually shied away from that. I'm very interested to see if people can come up with non-anthropocentric ways to convey feeling. But I think you're absolutely right that whether it's anthropomorphic or not, it has to have some kind of affect on board, because that's an interesting way to create reward for the kids.
Yeah, no, it's a great point. I think that there's sort of two issues that I guess we all sort of run into. One is a desire to sort of reduce complexity in order to, as Illa said, not have the thing break too many times. And every actuator, failure increases exponentially with number of actuators. But the other interesting point is I think that there can be interesting ways to have the system have people think that the robot's thinking, even if it looks like it's with relatively few actuators. I mean, people will anthropomorphize even simple systems that are doing obstacle detection and impute all sorts of nasty characteristics to them. And maybe one of the things that we could also look at is maybe displaying more emotion through smaller numbers of sensors, so smaller number of actuators.
I think some of our robots actually, when they have a camera on them and the camera's on a servo and you can actually see that the camera's looking at something, sort of approaches that a little bit. Also, I think another one we had a robot dance contest one semester in the class, and the girls actually had the best dancing robot in the group, which I thought was kind of interesting.
So I'm going to ask a question that's kind of in the technical weeds, but since everybody has more or less talked about the fact that they're designing a new robot coming out, the three of you did, I think, I see a lot of emphasis on a particular microprocessor that's going to have lots and lots of I/O, but in particular be wireless. But there's also been a lot of discussion about vision processing, which means you need powerful microprocessors, or you got to ship the whole thing off. And there's a lot of emphasis on cost, trying to drive low cost. I see these three things like all in opposition to each other. It's like, faster, better, cheaper. You get two of the three. And so I'm wondering, what is the argument against just putting a full-fledged computer on board? Because battery technology is good enough that you can drive like an hour without power and just get a very, very cheap microcontroller.
Yeah, I have a lot of sympathy with your point, Nick, but let's go down the line. I think there's some interesting views.
I guess we're just going on the line. Okay, right. Okay. I guess we have an order now. I believe that we can do so much of the low real-time stuff on board the robot now that we actually don't need to put a big computer on the robot. And I can make small desktop robots that run for a very long time that way. The thing I've been tending toward, which is the opposite of what I used to do, is I used to put everything on the robot. Now I'm putting everything off the robot that I can possibly put off the robot. So I'm literally doing the back EMF speed control on the robot, but yes, I'm shipping the images off the robot for processing off board. That means that I'm not going to be playing ping pong with my robot in real time, unless I put a vision processor that front ends that part of the object tracking on board. Rather, I'm going to do vSLAM off board on servers and then farm it out to all my robots as clients. So that's the dream we have, is to create a whole lot of different interesting vision servers off board. But that's a totally different architecture from what you're describing. I don't think there's anything wrong with doing it your way either. And in fact, I don't think that it's a dichotomy. You have to have the real-time stuff on the robot. I think you need to do the back EMF thing, so you don't need to use expensive encoders. And that pretty much demands an FPGA or a custom circuit. But beyond that, you would need the wireless. And unfortunately, there's no really good high-speed PIC wireless solutions right now, so I think the ARM chip is the cheapest way we can do wireless today.
Yeah, on our robots, I've sort of seen them fall into two categories. One where they want the most powerful computer they can get, another where they'd like to have a low-power processor. And, of course, that also impacts the base. How big is it? How long a battery life do you get? But I think that is an interesting point to think about. How much power do you really need? But if you're going to reuse all the parts, it's nice to have the most powerful processor you can, then it's going to work for all your projects.
Yeah, I actually very much resonate with what you're saying. I guess probably because I'm a vision researcher, and so as Jim mentioned, I think things sort of tend to fall into two camps. There's stuff that's sort of relatively small, but you want to do really fast, like low-level PID loop closure, or reading IMU data that might go up to a couple kilohertz. And on the other hand, you want to do vision processing or audio processing or or speech synthesis or something like that. So we've really sort of focused more on this idea of, okay, you're going to have a bunch of relatively cheap but really fast embedded PICs or microprocessors that can be networked to handle your low-level stuff, to be your spinal cord, and then have all the high-level stuff done on a x86 based system. That's really the way we're going.
So my question is, when we teach a very large class, so this, so from practicality point of view, is very difficult to maintain the class. I teach an embedded class of over 100 students. The equipment is going to kill you, basically. What I'm thinking about for this fancy robotics is we really need the realistic emulators. The students will, in large cases, work on the emulators, and by the end, when they figure out everything, they just put the real thing together. But not from the very beginning. They spend all the time to do the fancy mechanics. I know that's the part of the excitement, to do all this physics and mechanical work. But realistically, a semester is short. A class is huge. Yeah, we're talking about, I'm not talking about high-level classes, the low-level classes. If we want to do it, we need realistic emulators to get the student to do the most part of the work.
Everybody agree with emulation?
This is a good controversial one, so I appreciate the question. First of all, in many different kinds of classes, there's models for kinds of emulation and simulation. You use SPICE when you want to check out your circuit before you commit it. But the problem is that the interesting thing about the robot is the physical concrete item and the way it interacts with the physical world and pushes on the real world. And that's how you get the interest of the students who otherwise you wouldn't have gotten interested. So emulators simply, in my opinion, aren't going to attract precisely the students that you're hoping to attract with a new curriculum. My counterpoint to the idea that robots are expensive is I think we can end up with robots in high volumes that only cost a couple $100s. And that is a fraction of the amount of money that you're spending per computer for a computer lab. So all we're really talking about is making the computer lab 1.2 times as expensive as it is today and having robots in there along with computers. So in my opinion, it's a cost that's well worth just doing it, grinning and bearing it. And the result, the reward you get from it, I think, far outweighs the mere money.
Yeah, I think I'd have to agree with that. There was an interview with high school students that I read about, I think it was an IEEE Spectrum, and they asked some students about careers in electrical engineering. And the high school students said they didn't want to be an electrical engineer because all they do is simulate things all day on computers.
I guess I'll take a slightly different point. I mean, I think simulators have a really important role. I think systems like Gazebo are really great, and I think that they should be a part of the development, but not the entire part. I think there's something to be said for making the rubber hit the road, and there are things you're going to learn in doing that just have to be learned. So yeah, I'd say the physical implementation always has to be key. But practically speaking, you're right. I mean, you don't want people to be debugging their for loops on physical hardware when they can be doing it in software.
I guess my question is kind of similar to that. I just wonder if any of you have taught a course like CS1 based on robotics or on robots, whether you actually have the time to do all the things that the CS1 is supposed to do, in addition to teaching them. There's a learning curve to working with these things. I teach a course in robotics and embedded systems, but it's at a higher level, and that course works very well. But these are students who are more mature and know about programming, know about hardware, and I just wonder for novices how you can fit everything in.
I did do a CS1 course. Unfortunately, though, I did it the wrong way. I did it over a summer, and we had them every day for 8 weeks. So it was like a camp. And as a result, it doesn't transfer well to the real thing. In other words, I taught them programming using the robot. They had no other vehicle for doing the programming. It was a Java course. And it worked really well. But look, they had me hands-on all day long, 8 hours a day for 8 weeks. One could argue that that's a semester, but it's a tough argument to win. But the second point I want to make is that the question is CS1 exactly the right point for robotics to have this kind of entree? I had a long conversation with Eric Roberts about a month and a half ago about this at Stanford. And he was saying that the retention problem is actually CS2. He was saying that the retention problem is roughly the third quarter of the process, and that that's precisely the right place to inject the robot. And I'm starting to actually come around to that opinion, and that's the discussion I'd love to have, is where should the robot be injected? Is it really CS1, or is that just too basic, and is the right place sort of quarter number 3 or semester 1.5 of the process? I think that might be the right place for it. And there you can make an argument that it actually works quite well.
Well, in our curriculum, we've used it in the digital logic course, which actually comes after the CS1 course. But it did work out fairly well. We give the students a lot of IP for the more complicated stuff that we know they're going to get bogged down in, and then they just use that to solve a larger overall problem, and that seems to work well for us. Now, of course, we've got the FPGA, and we do logic synthesis with VHDL, and they actually have a computer core, which is all set up for them to make that work, and it can work.
Yeah, I haven't taught CS1, so I'm a bit at a disadvantage here. So, what I will say is that the experience I had with working with summer undergrads and so on like that, having a framework that people can plug into, where they're not necessarily doing stuff from scratch really helps and gives them a sense of making progress without having to necessarily learn all the nuts and bolts.
This will be the last question.
Yeah, robots are a wonderful platform for teaching embedded systems programming, and I'd like to ask, what do you think about what level of embedded system programming are robots feasible for? Programming in assembly, programming in RTOS, programming in higher level languages, or model-based programming? Which one?
Speaking for CMU a little bit, we've done programming in assembly, we've done programming in C for a PIC environment, an ARM environment, and a 6811 environment. And have we done a real-time system style for Andrew's Leap, or not really? Not real-time. So it hasn't been real-time. The issue is when you're doing an educational robot, really being real-time doesn't quite matter as much. And doing C for a limited memory processor like a PIC chip or 6811 is already really interesting in terms of the limitations you face. So that's kind of my favorite place to start for a bottom-up approach.
We've actually had experience with both. The first course, they program in a very, very simple assembly language for a very simple processor core. And in the more advanced course, we've used C, C++.
Yeah, I get to see the world from exactly the opposite end, in that I'm seeing higher level CS students, and their problem is that they don't understand generally what a volt is. That's an overstatement. But and there, being able to do things in a higher level language where okay, you can write this thing that looks like a Java statement or stuff like that, but it's going to cause down the field actuation, or you're going to actually see an image, and now it's an image, you can work with it. It's now back in a frame that you can deal with. That's very useful. It just takes that 2 weeks of figuring out how to deal with the interrupts out of the picture.
Thank you, gentlemen. I'd just like to wrap up the session. My apologies we didn't get to answer all your questions, but you know who we are. We're going to be here over the next couple of days, so please come and grab us in the various other sessions that we'll be doing in the corridors. It's been great talking to you. I think robotics is cool, good for education. Please go out and teach using robots. While I'm here talking about robots, I just want to congratulate Cornell University, who I heard today were runners-up in the World Champions of the RoboCup competition, running CE.NET. Thank you very much, team. Good job, and congratulations to them. The winners were the Free University of Berlin in Germany, who I don't think were running an operating system at all. So you go figure that out.